Previously, we looked at the inner product of a weight k modular form, absolute value squared, and then renormalized so that it was weight 0 by multiplying by this y to the k, with an Eisenstein series. And here it was a little bit more convenient to have an s bar here as our variable, because of course in the inner product there's a conjugate on this, so it just makes the notation a little bit easier later. And we found that this was something like a gamma function divided by some power of 4 pi times some Dirichlet series, sort of like a symmetric square L function. Maybe this was an squared over n to the s, maybe shifted a little bit. Where here these an's were the Fourier coefficients of our cusp form as such. And this was a great trick, right? That we had this inner product and we could express it as some Dirichlet series that we might want to study that might have been the thing that we were interested in ahead of time, and our inner product gave us access to this. Now this lecture is going to be about doing the same thing, but instead of f being a holomorphic cusp form, we're going to take f to be a Maass form. So when f is a Maass form, it has a Fourier expansion still, but the Fourier expansion looks a little bit different. The form that it takes, I'm going to write it just the coefficients as this row of n, and then we had a Whittaker function, which is y to the 1/2, and then a modified Bessel function of the second kind, and then we have, this is at IR, where we're going to say that this Maass form has eigenvalue lambda, which is, we're going to write it as s times 1 minus s, and we're going to write that as 1/4 plus r squared. So, i.e., s is going to be 1/2 plus I times r. And so this IR here parallels the s minus 1/2 that we see in the Eisenstein series. And then this modified Bessel function was evaluated at 2 pi times absolute value of n times y, and then we had an e to the 2 pi I nx. So this was our Fourier expansion of our Maass form. We can always write it this way. And what these Fourier coefficients are quite mysterious, but okay, they're there, and maybe we want to study them. And maybe we want to study them by putting them into some Dirichlet series. So let's try and get access to something like this using the same trick of looking at an inner product. So here, these Maass forms, I mean, they could have a character, but our absolute value squared of the Maass form, this is always going to be of trivial character, trivial Nebentypus, and this is weight 0, so we don't need we have y to the 0 here, if you will. And then let's just take the inner product with our Eisenstein series of the appropriate level, and let's see what happens. So by definition, this is the integral on the domain upper half plane quotiented by gamma naught n. So our Maass form will be of level n. And then by definition of the inner product, this is f of z times f of z bar, and then times e z s bar, and this is an Eisenstein series of level n. So if you want, you could write with the character to be the trivial Dirichlet character mod n. And then we have our usual measure, dx dy over y squared. This is the measure that's invariant under Mobius transformations. And now we can unfold this just like we did before. And when we unfold, we get this integral. Y goes from 0 to infinity, x goes from 0 to 1 of f of z times f of z bar, and then here we'll just have a y to the s dx dy over y squared. And now here we're going to do the same thing that we did in the previous example. We're going to replace both of these f of z's with their Fourier expansions, and then say, okay, what needs to happen if this integral in x is to not vanish? So let's rewrite this inner product here. Again, the integral y goes from 0 to infinity, integral x goes from 0 to 1, and then here I'll write this one, n not equals 0, rho of n, y to the 1/2 k I r, 2 pi n y, and I'm just going to write e of nx as shorthand for e to the 2 pi I nx. So that's going, this whole thing is f of z. And then we have our f of z bar that we need to write. So this is going to be multiplied by, it's going to be the sum, I'll use m for the sum here, m not equals 0. And we have a row of m conjugate, because we've got our conjugate here. And then y to the 1/2 k, and this will still be IR. When we take the conjugate, it would be minus IR, but remember that k of, if you have the k Bessel function evaluated at, say, v at y, this is equal to the k Bessel function at minus v y. And this was just immediate from this change of variables. T goes to 1 over t in the definition. So we get this, and then we have our 2 pi m y e, and here we have minus mx because of the complex conjugate. And then we have our y to the s dx dy over y squared. Okay, and now again let's ask what has to happen for this integral in x not to vanish. What we'll need is m to be equal to n for this integral of whatever e nx e minus mx dx to not be 0. So what that means is that our integral we can write it. I'm just going to bring out a sum over n here. So it's a sum n not equal 0. And then we have our integral in y from 0 to infinity, x from 0 to 1. And then we have rho n absolute value squared. So because we have a rho n here, and then we have a rho m here, then we have a y to the 1/2 times 1/2, so that's a y. And then we have our modified Bessel function at IR, because both of them are at IR. 2 pi n y, because m is equal to n, squared y to the s dx dy over y squared. And of course, we can just omit writing all the other terms because we know that those integrals will be 0. And then, of course, we see that there's no x dependence in this, so we can just drop that x dependent, that we can just integrate x from 0 to 1. Get the sum n not equal 0, and then I'm going to bring out the absolute value squared of this Fourier coefficient. And then we have our integral y going from 0 to infinity, and the power of y that we get is y to the s minus 2 plus 1. So we can write this as just our k Bessel function, IR 2 pi n y absolute squared times y to the s dy over y. That's pretty good. That's nice and tidy. And what we had previously for this piece was some exponential. And we could recognize that as essentially the melon. We could recognize this as a gamma function by definition. Here we can't do that, right? We don't know what this integral is, and we could work it out, but there's an easier way, and that is to just look it up. So in Grad Stein Rizek, let me make sure I'm spelling that right. Yeah, I think so. Okay. And the equation number is 6.576.4 gives the following identity, which comes up surprisingly often. And that identity appears somewhat terrifying, but it's all right. So the identity is if you have k Bessel function at u, ay times another k Bessel function v by y to the s dy over y, and there are going to be some assumptions on these parameters. What you need is that the real part of a plus b is strictly positive, and you need that the real part of s, let me write this on the next line, sorry, and you need that the real part of S is strictly greater than the absolute values of the sum, or the sum of the absolute values of the real part of U and the real part of V. Because if you don't have these, then your integral doesn't converge, and maybe you can still do something in that situation, but this is where this formula I'm going to write is valid, and what you end up getting after you look it up is that this is equal to 2 to the s minus 3 over a to the s gamma s times b over a to the v, and then you have a product of 4 gamma functions. So gamma of s plus u plus v over 2 times gamma of s plus u minus v over 2. And then you're going to have the remaining 2 gamma functions, gamma of s minus u plus v over 2 times gamma of s minus u minus v over 2. And then finally, you get this hypergeometric function, which is something we can explore at some point in the future when it ends up being a little bit more sensitive, and that's going to be the hypergeometric function at s plus u plus v over 2, s plus u minus v over 2. You have an s, and then the parameter, or the z, is 1 minus b squared over a squared. And so you may be wondering, what is this, right? What are you looking at? So the hypergeometric function, or this Gauss's hypergeometric function, this is defined by an infinite series, and so it's 2f1. That's ugly. This 2f1 is specifically with the 2 and the 1 is Gauss's hypergeometric function. And let me see if I can get a definition real quick. So the definition is that if you have p fq, or p and q are integers, and then what you have in the notation is you have complex numbers a1, a2, ap, and then a semicolon, b1, b2, bq, and then you have another semicolon, and then you have z. This is defined to be this infinite series. The infinite series is the sum k equals 0 to infinity of z to the k over k factorial, and then you have this ratio of gamma functions. So gamma a1 plus k, gamma a2 plus k, dot dot dot, gamma ap plus k, and then you have gamma of just b1 all the way up to gamma of just bq, and then in the denominator you have just gamma of a1 product all the way up to just gamma of ap, and then you have gamma of b1 plus k product all the way up to gamma of bq plus k. Okay, so it's some infinite series. And these things are studied a bunch because they come up a bunch. And with this series, you can do some analysis when you really need to, but one observation that is immediate from the series definition is that if you have a hypergeometric function and you have whatever here, and then you have whatever here, and then you have a 0 for your z, then this is necessarily equal to 1. Because the only term that's going to contribute is when k is 0. And then when k is 0, you get 1 over 0 factorial, and then because this k is 0, all these gamma functions, they all cancel out, and you just get 1 for this ratio. Now, if you want to know more about hypergeometric functions, and we will need to know more a little bit later, a nice place to learn about them is Gradstein and Rizek, section 9.1. And that'll define hypergeometric functions. It'll give you a bunch of identities. It'll give you a bunch of facts about how they behave. But in our situation, this observation will be sufficient, because if we look at, so here we have a general formula for the Mellin transform of a product of two modified Bessel functions, and the hypergeometric function we're getting, it's evaluated at 1 minus b squared over a squared. And in particular, if a and b are equal, then the hypergeometric function won't appear, and that is exactly the case here, right? A and b were the coefficients of y here, so we won't need to worry about it for this specific example. We will need to worry about it in the future, but not today. So what we end up getting once we use the formula for this Mellin transform, so what we'll have is that our u will be IR, our v will be IR, our a will be 2 pi absolute value n, and our b will be 2 pi absolute value n. And let's check the conditions. So the real part of a plus b strictly positive, yes, because our n is non-zero. And we will just need that the real part of s is strictly positive. So what we end up getting is that our inner product of the absolute value squared of our Maass form with this Eisenstein series evaluated at S bar is equal to the sum n not equal 0 absolute value squared of the Fourier coefficient of the Maass form, And then here we're going to use this formula to say this is 2 to the s minus 3. And then here we had an a to the s, and a for us was 2 pi absolute value n to the s, gamma of s. And then here we had, I'll write it for emphasis, a b over a to the v. So this is 2 pi n over 2 pi n, and then our v was ir. But of course this term is just going to be 1. And then we had our gamma functions. So this is gamma of s plus, so u and v were both ir, so this will be plus 2 ir over 2. And then the second gamma function, it's going to be s plus ir minus ir, so it's just going to be s over 2. And then we're actually going to get 2 of these, right? The s minus u plus v also gives an s over 2. And then we get our gamma of s minus 2ir over 2. And then, as we talked about, we get whatever this is here with a 0 here, and this is also just 1. So let's maybe clean up a little bit. That this inner product is, I'm just going to rewrite exactly the same thing. So we have sum n not equals 0, rho of n absolute value squared. Now this 2 to the s here is going to cancel this 2 to the s here. And so what we're left with is, so let's write this product for gamma functions. Gamma of s over 2 plus ir times gamma of s over 2 minus ir times gamma of s over 2, it's a little bit unclear, is gamma of s over 2 squared. And then in the denominator, we have this, well, maybe the n to the s, we should put it here. And then here we have this divided by 8 coming from 2 to the minus 3. So we have 8 pi to the s, and then we have a gamma s from this. And this is the identity that we get, that our inner product is equal to this thing. And now here, we're again quite lucky, there is no n dependence here. We're not going to be this lucky every time, but we are this lucky this time. So let's recap. If we take the inner product of the absolute value squared of some Maass form with the Eisenstein series, evaluated at s bar, then what we end up getting is gamma of s over 2 plus ir times gamma of s over 2 minus ir times gamma of s over 2 squared divided by 8 pi to the s gamma s times, and now here what we can do is we can say, hey, this is, if we have n goes to minus n, well, we know that rho of minus n is either plus or minus rho of n, depending on if the Maass form we have is even or odd. And what that means is that the absolute value squared is the same, so we can actually take the sum from 1 to infinity and then double it. So let's take this 8 and let's turn it, so this is going to be 2 times the sum n from 1 to infinity, so this will replace this with a 4. And then here we have a sum n from 1 to infinity of absolute value squared of rho n times n to the s. And that's pretty good. I mean, so this thing, again, it sure looks like an L function. And we might be interested in the statistics of these Fourier coefficients rho. And this inner product seems like a good way to get access to this. Because if we can study this inner product in other ways, then we can understand this L function. And these gamma factors that appear in front, these are things that are pretty easy to understand. We know a lot about the gamma function, so we're pretty happy to just see some simple product of them. That should be no problem at all to understand for whatever purpose we're looking for.